how to develop expression for the displacement for a cantilever bar subjected to uniform axial load using weighted residual approach. Let us discuss in this video. Okay, so this is a cantilever bar which is subjected to an uniformly acting axial load. Okay, so the magnitude of the uniformly subjected axial load is taken as Q0. The length of the cantilever bar is given as L, and the deformation is experienced along the x-axis. Okay. So we know the governing differential equation for one-dimensional bar element. Governing differential equation for one-dimensional bar element is AE d square u by dx square plus Q0 is equal to 0. Here in our problem, this differential equation is applicable between the limits 0 to L. Okay, and the boundary conditions of the given problem. Boundary conditions: since the given bar element is fixed at the leftmost end, so at that position at x is equal to 0, the displacement will be 0. So this is an essential boundary condition of the given problem. Okay, so next, at the end of the bar there will be no strain under the loading condition, so that may be considered as a second boundary condition. Strain E is equal to du by dx at x is equal to L. At the end of the bar there will be no strain. Okay, so these two can be considered as the boundary conditions. While solving the problem, these boundary conditions will be directly given in the problem. Okay, but we have to know these are the boundary conditions for a cantilever bar subjected to axial loading condition. Okay, so to solve any structural problem, any kind of structural problem using weighted residual approach, we have to follow certain standard procedures. So first, at the initial stage, we have to select a suitable trial function which should satisfy the given boundary conditions of the problem. So that is the main step and the initial step. So we have to choose a suitable trial function. So usually for simplicity, polynomial type of functions are considered as trial functions. Okay, so after finding out the suitable trial function satisfying the boundary conditions, we have to raise the trial function to the given governing differential equation of the structure, and by equating those two we will get the residual value. Okay, so then residual should be equal to 0 to get the required answers. And following them, different types of weighted residual approaches are there. So in each approach, the residual will be equal to 0 subject to certain conditions. So let us discuss in this lecture video about the standard procedure of weighted residual approach. So first, let us consider the trial function . So here u is the displacement. So u of x can be considered as a0 plus a1x plus a2x square. So this is a standard polynomial function a3x3, so which continues. But for the given problem, since the order of the governing differential equation for bar element is 2, it is enough to choose the polynomial function with order 2. So a0 plus a1x plus a2x square. So we can keep this as equation 1 and this as equation 2. So we have to frame this trial function to be suitable for the given function, given problem, that is, this function should satisfy the given boundary condition. So first apply the first boundary condition in equation 2 to completely modify this standard displacement function as the displacement function for our problem. Okay, so by applying each boundary conditions one by one into the equation 2 standard trial function, we can modify the displacement polynomial function as the required displacement function. Okay, so by applying the first boundary condition, that is, while we subject the value of x to 0 at x is equal to 0, the displacement will be 0. So equation 2 becomes a0 plus a1 into 0 plus a2 into 0 is equal to u equal to 0. Okay, so a0 will be 0 when we are applying the first boundary condition. So then to apply the second boundary condition, we have to have the displacement function in its differential form. Okay, so differentiate equation 2 with respect to x. So we can get the value for du by dx. So a0 is a constant value, so the differential form will be 0. However, the a0 value is 0. We have already found out in the previous step. Then the differentiation for the second term a1x. So a1 is a constant value. X, the differentiation for x is 1 with respect to x. Then for the third term, that is a2x square, a2 into 2x. Okay, so we can keep this as equation 3. So now we can apply the second boundary condition in equation 3. Okay, so apply the second boundary condition in equation 3, that is du by dx at x is equal to L is equal to 0. Okay, so a1 plus a2 into 2L is equal to 0. Okay, so a1 is equal to minus 2a2L. So by applying both the boundary conditions for the problem we have considered into the chosen trial function, we have found out the values of a0, a1 and a2. So substitute a0, a1 and a2, the found out values for a0, a1 and a2 in equation 2. So u of x will be a0 value is 0 plus a1 is minus 2a2L into x, a1x plus a2x square. Okay, now we can keep a2 outside. So x squared minus 2lx. So this is the trial function for the present problem. Okay, so we can keep this as equation 4. So this is the trial function which will definitely satisfy the given boundary conditions. Okay, so now in the next step we have to formulate the residual function. For that we have to raise this function presented in equation 4 to the order of the governing differential equation. So the order of the governing differential equation for the considered problem is 2. AE d square u by dx square, the order is 2. So we have to raise this equation to order 2. So by differentiating the above expression once with respect to x, a2 into the differential form for x square is 2x minus 2lx, 2l. Okay, by differentiating again the above expression with respect to x, d square u by dx square is equal to a2 into 2 into 1 minus the differential form for the constant value is 0, so 2a2. Okay, so that is d square u by dx square is 2a2. Okay, so now by comparing this with the actual governing differential equation, we can formulate the residual function. So here we have that d square u by dx square value is 2a2. Just substitute this value in equation 1. Okay, so in the place of d square u by dx square, we can put as 2a2. Okay, so ae into 2a2 plus q naught. So this will be the residual function for our problem. So to get the exact solution, the residual value should be 0. There should not be any residual for getting accurate solution. Okay, if we consider the exact trial function, then when we are comparing the residual function, when we are comparing the trial function with the governing differential equation, there will be no residual. Residual means balance. If we consider the trial function as the exact displacement function, then there will be no balance in the result. Okay, if we have some residual, if we equate that residual to 0, then we can have the result nearer to the accurate result. Okay, so in the first method of weighted residual approach, that is called as point collocation method, residual will be directly equated to 0 to get the required answer. Okay, so ae into 2a2 plus q naught is equal to 0. So ae 2a2 is equal to minus q naught. a2 will be minus q naught divided by 2ae. Okay, so we have the trial function in equation 4 as a2 into x square minus 2lx. Now by following the first method of weighted residual approach, that is point collocation method, we have found out the value for a2. So now we can substitute that a2 value in this equation. So u of x is equal to minus q naught divided by 2ae into x squared minus 2lx. Okay, or simply we can write like this, that is q naught by 2ae into 2lx minus x square. So this is the required expression for the deformation in the given cantilever bar subjected to axial load.